I'm going to do an example of calculating the curvature from the definition. As the book points out, that's not always the most efficient way to do it, but we're not going to go into all the intricacies of all the different formulas. It gets kind of bewildering, and it's not our main focus. But I'm going to do number 18 here from the book, and it's a bit contrived. We've seen that in order to make some of these things work and get all the calculations to work out nicely, the examples have to be kind of contrived. Now, for the other alternative formulas, they don't have to be as contrived. But here's a good one to start with. So that's r of t. That's our function. And if you look at this, I invite you to go ahead and plot this on the applet. What happens is this gives you progressive motion that's getting increasingly fast in the t variable as t goes on. These give you, like the t cosine t sine would give you like a spiraling outward. But it's not spiraling outward as much as this is going fast. So what happens is it kind of gets stretched out. Roughly, if that's the x variable, let's say that's y, and that's it sort of starts, roughly it's kind of coiled in and then kind of gets, well, less and less coiled, and so it gets straighter. What we expect to see is the curvature decreasing. I can't do justice to that real quick, so I'll have you look at the applet. So let's go through the process here. The first thing you need is the velocity, and if you calculate that out, when you use the product rule here, you get two things, but one of them exactly cancels with this, okay? And so what you get is something rather simple. You get t sine t. And this one also has a cancellation. When you differentiate the t, you get sine t, and then a minus sine t from here, and so those cancel, and so we end up getting t cosine t. Go ahead and check it yourself. Stop the video and check it yourself if you don't trust it. So, the definition says, don't pay attention to the velocity, pay attention to the unit tangent vector. So we need to make this unit vector. So in other words, to do that, we've got to first figure out the magnitude of the velocity, and of course that's magnitude of r prime. Now it's got a common factor of t in it, and then it's going to be square root of 2 squared plus sine squared, hey, this is looking good, plus cosine squared. And that's the heart of what's contrived about it. That's 1, so you get root 5 times t. That's a very simple speed profile. Even though it looked complicated, it was designed to have this simple speed profile. So the unit tangent vector you get just by taking this velocity vector and dividing by this guy. The t's are going to cancel out, and I'm just going to get a very simple unit tangent vector when expressed as a function of t. Okay, so now I take the derivative of that. Now ideally I would be taking the derivative of that with respect to position. Remember, I'd like to get, let me review that just a little sec. It's in the book, but let's look at that. I'd like to get dt ds, and then take the magnitude of that vector derivative. This would give me the vector rate of change as I walk along at a certain rate on the curve at unit speed, basically. This guy doesn't go at unit speed. So ideally, I would reparameterize with respect to arc length. We've seen how difficult that is in general, and I wouldn't want to try to do it for this, although it'd be possible. So the clever thing is to realize that changing variables in derivatives is actually really simple because of the chain rule. This is going to be dt dt with respect to time times dt ds. It's just a chain rule calculation. Now this is a little weird though, because this is exactly 1 over the speed. What we really want is ds dt, because that's this guy. So the speed actually comes in two crucial ways here, and we'll see a nice theoretical result of that next time. And so what you get is the formula in the book. It's the rate of change of, you go ahead and take the rate of change of the unit tangent vector with respect to time, but then you correct for the fact that that's not the variable you wanted by dividing by the speed. And so you take t prime of t over r prime, the magnitude of r prime, and then we're going to take the magnitude of that guy. So we're just going to take magnitudes everywhere, because what we really mostly care about You can use the vector, it's cool, but mostly we care about the magnitude of that guy. Okay, so let's continue with our example. That means we can take t prime with respect to little t. The 1 over root 5 comes out. You just differentiate all three. This is coming from here. And we're almost done, because then we just have to divide that. Oh, let's take the magnitude of that guy. So again, constant factor comes out of a magnitude. And hey, look at that. It's a unit vector. How nice. Not always going to happen, certainly. So that's 1 over root 5. And now, so our curvature is going to be magnitude of t prime of t divided by our correction factor based on the fact that I was differentiating with respect to t, and I really wanted to be differentiating with respect to s. And so that's 1 over root 5 over root 5t. So it's 1 over 5t. And again, if you look at the applet, you can kind of convince yourself that this is something that starts out really, really highly curving, and then getting less and less and less curved as time goes on. Now, one thing here is that what about it as t goes to 0? The curvature seems to go to infinity. Let's say from above. That's interesting. It's getting infinitely curved. Is that really true? Well, let's think about what happens with the speed of this curve. And this is going to be a good entry into something that I alluded to before with an example, but it's been a few days, and I wanted to come back to that. That the speed of this curve, root 5t, it's a simple expression, but notice when t equals 0, it slows down and momentarily stops. And what that means is it has the ability to change direction. When you momentarily stop, you can do things like throw it into reverse or change direction instantaneously, essentially. And that means you can put a kink in it, you can make it infinitely tight, you can do all kinds of things. And that's what's reflected here, that the curvature is going to infinity. Let me go back to a simpler example of that, where we had t cubed t squared. We looked at that example, and it looked like this. It had a cusp at t equals 0 at the origin. And both of these are examples of curves that are not smooth at t equals 0. And if you look in the book, the definition of a smooth curve, there's part of it that's fairly reasonable. It requires that all the functions, the component functions, be differentiable, and so that you have a nice velocity vector everywhere. But it also requires that that velocity vector not be 0. And you might think, why is that so bad? It's because, one reason is, if you slow down and stop, you can go off in a totally different direction, and you're going to put a kink in the curve that won't be detected by just looking at whether these functions, or in this example, these functions, are not differentiable. They are differentiable. The velocity function is perfectly nice. In terms of, is this a physically realizable thing for a particle to do? No problem. You're not going to get an infinite acceleration. Here's the acceleration. 6t, 2. That's a nice, perfectly nice set of vectors. But the track that it does is going to be weird. And another way we could say it is, suppose you reparameterize this with respect to arc length. Would that require infinite acceleration? And that would, because in an extremely short space of source of distance, you're radically changing your direction. But not, according to this guy, in an extremely short space of time, because you slow down and you momentarily stop there. Let's see what happens if we try to calculate, well, I don't know if we have time. If we tried to calculate the curvature there, we would be dividing by the speed, but the speed, again, turns out to be t times root 4 plus 9t squared. That dies at the origin. Okay, at t equals 0, which is the origin here. And that's what happened here. The problem here was not so much with the t prime of t. That never blew up. But because the speed went to 0, we got infinite curvature. Similarly, that cusp is a point of infinite curvature. So that's why the definition of smoothness for curves includes a stipulation that the velocity not go to 0.